Hello, and welcome to Lighting for the Future, an AIA course on how LED lighting is changing the role of building lighting design. I'm Grayson Evans, an independent technology consultant, and I'll be taking you through the course. I've worked in the building technology business for 20 plus years and created and delivered education to that industry for another 20 plus years. During this course, I'll be covering how LED lighting works and the lighting opportunities it presents, the effects of natural and artificial light on human circadian rhythms, health, and well-being, and how to take advantage of new LED technology to incorporate healthier lighting strategies into your building designs. The majority of building lighting is transitioning to LED technology. The advantages, which we'll cover, include much less power and heat, a wide gamut of colors and spectrum, small form factors, and the ability to improve the occupant's health. But there are disadvantages. If care and planning are not used in specifying LED lighting, it can look really bad. It can have problems dimming with flicker, there's a lack of power and control standards, and it's generally higher cost, at least for the short term. But because of their small shapes and size, low voltage, and cool operation, LED lighting opens up a whole new world of lighting possibilities previously not possible. To work with existing infrastructure, LED lights are primarily available as incandescent replacements, like these screw-in base types, and even twist-in fluorescents. Most of the size and expense of these lights is due to the power supply that converts conventional 120 volt AC into low voltage DC for the actual light emitting diodes. Optional dimming electronics must also be included to support conventional wall dimmers. LED fixtures are also available that directly substitute for conventional incandescent in-ceiling types, again with built-in or attached power supply electronics. But there are a wide range of low-voltage native and 12-volt replacement bulbs designed to fit existing connector types. A new style of low-voltage LED strip lights, available in many colors and brightness levels, is commonly available. These are made from individual LED emitters directly attached to the flexible strip. Strip lights have created the opportunity for incorporating lighting into new shapes and applications, such as the curved fixture on the right and the stairs on the left. Each stair has 4 separately controlled, full-color LED strips sandwiched between 2 layers of frosted glass. They're controlled by stage lighting software in a dedicated computer. This was one of my projects in Turkey. LED strips are also available as part of metal interlocking channels that can be installed almost anywhere, such as behind mirrors or TVs to create a floating effect, around doors to help the elderly find their way, along baseboards to illuminate walkways, and to provide wall wash or other decorative effects. Controlling and powering LED lights has also been changing, from traditional high-voltage lighting automation systems to low-voltage bus systems, including the same Ethernet bus that provides the building data backbone, to wireless technology built right into the LED bulb. In traditional high-voltage lighting control systems, lighting loads are wired directly to a central load control system. These systems control the on-off and dimming functions, but can usually be adapted to basic control of LED lights at much lower power. Traditional distributed control systems use in-wall smart wall switch replacements, wirelessly connected to a control system that handles the on-off dimming functions. They can directly control certain LED replacement lights. But many newer LED fixtures are designed to use bus technologies such as Dolly and DMX, very popular in Europe but only recently gaining acceptance in the US. The bus wiring supplies both low voltage power and control signals. DMX was originally designed for stage lighting control and can handle the full color control at each light. The bus allows individual lights to be controlled without having to wire them separately. For small commercial or residential lighting, there are now several types of LED lights with built-in wireless connectivity. They can be controlled directly from an iPad or smartphone using the existing wireless network. Great for retrofit wiring applications. But probably the most interesting advance in lighting control is lighting fixtures that connect directly to the wired building data network. The Power over Ethernet standard allows devices that connect to the network to get their operating power directly from the network, such as wireless access points, cameras, music devices, and so on. But because this standard has been upgraded to deliver more power, this now includes LED lighting fixtures. Fixtures are attached to the network like any other low-voltage network device. Power over Ethernet network switches provide both the power and control signals over low-voltage Class 2 network wiring, such as Cat5 or Cat6. These can be installed by any low-voltage contractor. High-voltage wiring is no longer needed. Lighting control systems incorporate newer wall-mounted keypads as the user interface. They come in a wide variety of designs, even full-color LCD touchscreens, fully customizable for the client. As well as iPads, fully customized wall-mounted touch panels, handheld controllers, and of course, smartphones. All lighting control systems that I'm aware interface to or are part of home and building automation systems. So lighting scenes, including the level and the color, can be triggered by time schedules, security devices, occupancy, outside light levels, and so on. To get into some of the more advanced lighting topics, you really need to understand a bit more about how LEDs work. Well, at least I think you do. How they produce white light, how they dim, and how LED color is created and specified. LEDs are very low voltage devices. They can work fine from a single AAA flashlight battery. When energized with a voltage producing a current flow across their semiconductor parts, they emit a single wavelength of light, such as a shade of red, yellow, green, or blue. Since white light is a combination of all colors, a single LED can't produce white light. Creating white can be done in one of two ways. Color mixing, like you see here, combines red, green, and blue in our eye, so we see white. This technique is how TVs and LCD monitors produce color, including white. Their screens have millions of tiny red, green, and blue liquid crystal points, or LEDs, that merge together in our eye. The other way to make white light is what's called a blue pump. If you notice white emitting LED sources, you'll see a yellow-orangish looking material. This is called cerium-doped yttrium aluminum garnet, or YAG, or YAG for the rest of us. Underneath this is a blue light emitting LED. The emitted blue light is absorbed by the YAG phosphorus material that re-radiates light in the orange-yellow spectrum. Pretty cool, huh? This is a graph of the output color spectrum of a white LED. The LED emits light in the blue part of the spectrum, and the YAG puts out light from the green through the orange part of the spectrum. This type of graph is also called a spectral power density graph, or SPD. You may see this in manufacturers' data sheets. Notice that there is a dip in light output between the blue and the yellow. This is called the blue gap, and it's a problem with LEDs that we'll talk more about later. This is a graph of the human eye color sensitivity of the red, green, and blue cone cells in our eye. If I overlay the white LED output, you can see it provides enough energy within the red, the green, and the blue wavelength bands to appear white. Now let's cover a little bit about dimming, the LED's little secret. Unlike incandescent bulbs that easily dim with a reduction in voltage, LEDs don't. So we have to improvise. There are two techniques in use to dim an LED. The easy one is just to reduce the electrical current through the LED. But the problem is LEDs don't linearly dim with a reduction in current, as this little demo can show. I'll slowly and smoothly reduce the current through the LED, and you can see that it doesn't change brightness much until the very end when it abruptly dims to off. The chart tracks the brightness as the current is reduced, so you can see the problem. This technique is sometimes used for high power LEDs. The other more complicated but more common technique is called pulse width modulation, or dimming by tricking the brain. The LED is actually not dimmed at all. The trick is to turn the LED on and off very fast. The LED in the demo is connected to a device that controls the on time versus the off time, called the duty cycle. The scope on the right shows the actual voltage applied to the LED during the on versus the off part of the cycle. Our brain thinks the LED looks dim when it's on for only a short time and looks brighter when it's on for a longer time. This technique does give a smooth and fairly linear dimming response. The LED bulbs that dim have the electronics built in to convert traditional variable voltage dimming to a variable duty cycle. It does have some problems, as you can see in the flickering effect when filmed with the iPhone. Now that you know how LEDs work, I can introduce you to the current trends in LED technology, including dim to warm, tunable white, full color tuning, and melanopic stimulation. Whoa. But first, I need to make sure you understand color temperature. This will only take a couple of minutes, I promise. This diagram, called a chromaticity diagram, is used by graphic, lighting, and interior designers and others to specify colors and gamuts. It represents the full spectrum of colors that the eye can see. But understand that the diagram you see here on the screen can't reproduce all the colors the diagram represents, because the screen you're watching can't reproduce the colors listed on the chart. It's just an approximation. The numbers around the outside of the chart represent the wavelength of color at that point in nanometers. We can see roughly between near infrared at 780 nanometers up to near ultraviolet at 380 nanometers. The numbers on the X and Y axis allow a designer to specify any color on the diagram with just two numbers, similar to a Pantone color number. The dashed line that runs through the center is called the black body curve and represents the wavelength or color of light emitted by a black body, such as a piece of coal, as it's heated to increasingly higher temperatures. The line shows temperature in degrees Kelvin from less than 1,000 degrees to above 10,000 degrees, from deep red through white to blue-white. The color of the sun, for example, is represented on the curve at about 6,500 degrees. The range of color temperatures from roughly 3,000 to 7,000 Kelvin are considered white, even though the chart doesn't show that very well. Incandescent bulbs give off warmer colors because they actually operate at the lower temperatures on the curve. LEDs don't generate any heat, so their color is artificially manipulated to produce a color temperature on the curve. This gives them great color flexibility. The diagonal lines represent correlated color temperature, or CCT, a term you'll hear often with LED fixtures. Light sources that lie on the same CCT line share the same color temperature even though they're not the same color. So two LED sources with the same CCT may emit slightly different spectrums. LED lights are manufactured with a specific color temperature, ranging from 2000 or less to 7000 or more. Light given off by lower color temperatures is referred to as warm, and higher temperatures as cool. Now this can be confusing since warm colors have a cooler color temperature. Go figure. Color temperature is determined by the color spectrum generated by the LED. Warm colors emit more yellow to red wavelengths and less blue. As the color temperature gets higher, the spectrum is altered to produce more and more blue light and less of the longer wavelengths, orange and red. Understanding color temperature and its associated spectrum is really important for understanding the effect that a given light spectrum has on the appearance of materials. The presence of a color in the lighting spectrum means those colors will shine, while the absence will make those colors dark or black. For example, warm natural tones look better in a warm or cooler CCT spectrum. Early use of LED lighting, which lacked this understanding, gave LEDs a bad reputation among interior designers and clients. When dimmed, incandescent light sources get physically cooler in color temperature, but we say they look warmer. Most designers and occupants are used to this effect and like it. Unfortunately, LED sources, when dimmed, output less light, but at the same color temperature. It doesn't look natural. To correct this, LED light manufacturers have created what's called dim to warm lights that simulate the incandescent color shift. When these bulbs are dimmed, they smoothly shift their color spectrum to a lower color temperature, as you see in this scene. How much depends on how the manufacturer implements the effect. High quality, dim to warm bulbs will track the black body curve as they're dimmed. This is usually done by having two or more LEDs in the bulb, one with high color temperature, the other with low color temperature. Dimming gradually shifts the light output from one to the other while also reducing the light output. Having multiple different temperature LEDs in the same bulb or fixture allows what is referred to as tunable white, meaning they can independently change the illuminance and color temperature. These devices require separate control inputs to select brightness and color temperature. As we'll see shortly, this technology allows the lighting designer to simulate natural outdoor light changes throughout the day. Tunable white also relies on a mix of several different LED types and spectra in the same device. The goal in tunable white is to keep the spectrum on the black body curve throughout its tuning range while maintaining the same illuminance. A user interface for tunable white will need a way to control the illuminance and the color temperature separately. Tunable white spectrum can also be created using full color fixtures that have the control electronics built in. Full color tuning is a feature of an LED fixture that has red, green, and blue LEDs built in. By varying the intensity of each primary color, a wide range of colors and intensities can be created. While primarily decorative, full color lighting has become very popular and easy to use with new wireless interfaces. The reason all this color temperature stuff is so important is that for the first time, architects, lighting, and interior designers can recreate the natural lighting cycle of our planet. And the reason this is so important is because we now know for the first time that you have the ability to directly influence clients' health. It's all about our circadian clock. Over the past 10 years, researchers have unequivocally determined that human body functions operate on a 24-hour cycle called their circadian cycle. It's a free-running clock that must be synchronized and reset each day, and natural light is the mechanism that does it. There are many important circadian internal cycles or rhythms that keep us in sync with the solar cycle, but 3 directly affect how we sleep and work. The melatonin hormone cycle controls our sleep. Melatonin production is very low throughout the day, rising sharply in the early evening as the natural light level decreases, is at a maximum of about 3 a.m. during our deepest sleep, and decreases rapidly at the first morning light. The cortisol hormone cycle is responsible for our alertness. It's dormant throughout the night, but rises sharply before dawn and keeps us alert during the morning hours, decreasing in the afternoon as natural light decreases. Our core body temperature also varies throughout the day, rising to a maximum about 6 p.m. and slowly decreasing to our deepest sleep time, and gradually rises with morning light. If you have ever experienced jet lag, you know how it feels to get these cycles out of whack with local daylight cycles. In reality, there are many more cycles and timekeeping clocks in the body. The activity of over 150 genes is affected by our circadian cycle, which is synchronized or entrained by the solar cycle. The synchronizing process is controlled by neurons in our eye. Light entering the eye activates melanopsin, a blue light sensing protein in the ganglion photoreceptors in the outer layer of the retina. These blue light sensing neurons, not part of the visual system, are the body's light meters and are hardwired to the master clock in the brain in the hypothalamus. This region of the brain synchronizes the hormone cycles and hundreds of other clocks throughout the body. Researchers have determined that it's not just any light that triggers our circadian cycles, but a specific band of wavelengths, amplitudes, and durations. It requires blue light around 480 nanometers at a level at our eyes of at least 100 lux for at least an hour to activate melanopsin. The reason for this wavelength might be explained when you compare it against the sun's spectrum. It falls in the region of the sun's maximum visual power output, and is why the ganglion photoreceptors are often called the blue sky detectors. The problem with most existing building lighting is that indoor daytime light levels and evening and nighttime light levels are too similar, causing circadian confusion. The best way to improve this situation is to provide a circadian daytime and nighttime lighting design, even if it is just as simple as creating brighter circadian days in a 9-to-5 workspace or home office and darker evenings. However, when you look at the spectrum of incandescent lights, it's easy to see that they provide very little circadian light. Neither do most fluorescent lights. Even LEDs come up short in the required spectrum due to their blue gap, but their spectrum can be adjusted to provide more blue light in the 460 to 480 nanometer region. But how much circadian light is adequate in different work or home environments, and which LED fixtures provide the best light? Standards are just emerging on recommended levels. 2 circadian lighting research groups are developing recommendations for quantifying circadian light in terms of spectrum, illumination, and timing. Melanopic Lux is part of the Wellbeing Institute Wellbeing Lighting Standard, and circadian stimulus was developed by the Lighting Research Center at the Rensselaer Polytechnic Institute. The Well-Building Institute has developed a method to quantify the effectiveness of a light source to provide light primarily in the 480 nanometer region by direct measurement of the spectral power density. This is called the equivalent melanopic lux ratio, or melanopic index. The index roughly quantifies the contribution of the light's spectral power density in the 480 nanometer band. This is derived by multiplying the regular lux intensity by the melanopic index. This gives the equivalent melanopic lux and is always a fraction of the overall visible lux. For example, if a light source has a rated output of 250 lux and a melanopic index of 0.65, then the equivalent melanopic lux is 163. This provides a guideline to compare different light sources for their effectiveness at providing circadian entrainment. The higher the index, the better. However, the index is calculated only for a given spectrum at a given color temperature. The Well-Building Lighting Standard recommends that the vertical lux at eye level in a work environment have at least a 200 equivalent melanopic lux, or EML, for 4 hours in the morning and at least 150 EML for the entire workday. In living spaces such as homes, 200 EML during the daylight and less than 50 ml during the night is what's recommended. The Lighting Research Center, LRC, has developed a similar, but in my opinion, a more rigorous set of guidelines. CLA is a measure of the total circadian light, primarily in the 455 to 465 nanometer spectrum. From this, they derive what's called circadian stimulation, or CS, a relative scale from 0.1 to 0.7, and represents the actual percent of melatonin suppression from 10 to 70% after a 1-hour exposure. A CS of 0.3 is the minimum circadian light that's effective for entrainment, with 0.7 being a saturation of circadian light. Most existing LED light sources are in the range of 0.1 to 0.4. Note that a CS of 0.3 and an EML of 200 are nearly equivalent. The LRC recommends a daytime CS target of 0.3 to 0.4 and an evening target of less than 0.1 for effective circadian synchronization. This graph is one of many proposed 24-hour lighting strategies for promoting circadian entrainment or synchronization that maximizes circadian stimulus during the day and minimizes stimulus at night, yet still maintains appropriate levels of light for visual performance. It's important to understand that CS levels are independent of illumination levels. This chart assumes a visual horizontal illumination level of 350 lux maintained throughout the day, while the melanopic illumination level changes throughout the day. This graph is one of many proposed 24-hour lighting strategies for promoting circadian entrainment or synchronization that maximizes circadian stimulus during the day and minimizes stimulus at night, yet still maintains appropriate levels of light for visual performance. It's important to understand that CS levels are independent of illumination levels. This chart assumes a visual horizontal illumination level of 350 lux maintained throughout the day, while the melanopic illumination level changes throughout the day. One of the difficulties to correctly specifying circadian lighting is the fact that different lights can have the same color temperature with entirely different spectrums. This graph shows the spectrum of two different lighting fixtures, both with the same color temperature of 2729 Kelvin. The fixture on the top with the red graph requires 575 visual lux to produce a 0.3 circadian stimulus. whereas the fixture on the bottom can produce the required 0.3 stimulus with only 240 lux output. The difference is primarily due to the location of the blue gap. The amount of lux illumination does not mean it produces a lot of circadian stimulus or melanopic lux. Obtaining spectral power density data, much less melanopic index numbers, on traditional LED fixtures can be challenging, since that information is typically not part of typical data sheets, and manufacturers are reluctant to provide it. But this situation is rapidly changing. Several manufacturers have created new LED chips with LED semiconductor materials that output a lot more blue light in the gap region around 480 nanometers. These new chips are also more power efficient, reducing the power requirement by as much as 50% to 160 lumens per watt. By using a combination of chips that produce high circadian stimulus light and chips that produce almost no circadian stimulus, newer fixtures can provide full circadian lighting throughout the daytime and nighttime work schedules. There are at least 30 companies that currently provide fixtures that use this technology. A simple strategy may be to use a combination of spectrally optimized LED fixtures during periods that require a high circadian light level, and transition to traditional LED fixtures later in the day or in the evening. LED fixtures that output little or no light in the 460 to 480 nanometer band still provide adequate blue light for good visual color definition, but not enough, especially when dimmed, to provide melanopic stimulation. If you have access to a specific light source or want to verify an installation, there are several inexpensive DIY tools on the market to measure SPD over the visual range directly. This information can be used to calculate melanopic index or circadian stimulation for a fixture at a particular color temperature. Regardless of the methods used to derive circadian light, there's no question in the lighting research community of the benefits of circadian lighting applied at the correct levels and times. Increased sleep efficiency in older adults, including those with Alzheimer's disease, relief from symptoms of seasonal affective disorder, increased alertness at all times of day and night, and improved cognitive performance. That's just to name a few of the benefits. But designing for year-round lighting that meets WELL or LRC minimum requirements is definitely new territory for architects. A good design should account for spectral power distribution from glazing, materials, daylight, electric lights, computer displays, as well as accounting for low daylight illumination and shade deployment. I put together some guidelines and more specific suggestions for 4 typical building environments to get you started: senior care, schools, offices, and healthcare facilities. Regardless of the project type, these are some general guidelines and recommendations that should always apply. Probably the most important is to make your client aware of the established health benefits of circadian lighting and how to use it properly. General awareness of circadian lighting is pretty limited, so this is probably your biggest hurdle. We have all been through new technology awareness curves before. In any design, use sunlight as much as possible. It can contribute more than 50% of melanopic light requirements. You can increase levels of melanopic light in areas that can't get enough sunlight with task lighting. It can contribute 20% of the required melanopic light. Choose newer, spectrally optimized fixtures that output a lot of light in the 460 to 480 nanometer band. When possible, use lighting that will tune from high melanopic light to low melanopic light, not just visible light. If you can't, specify banks of different spectral lighting that can be independently turned on and off to control the timing of circadian stimulus. Incorporate lighting control systems that time the illumination and spectrum to a circadian cycle. Add circadian stimulus or melanopic index levels to illumination requirements in lighting specifications. Circadian effective lighting is concerned with light that gets to the eye. Specify light levels measured in the vertical plane at eye level. And don't forget that the absence of light in the evening is just as important as a lot of light during the day. Keep melanopic light levels as low as possible after 6 p.m. It also helps just to dim lighting after that time as well. Let's start with the office. They have some design advantages since people generally sit at the same location for long periods, thus allowing more accurate estimates of long-term melanopic light exposure. It's been shown that supplemental LED task lighting at desks can be effectively used to increase melanopic light by 25% or more. When able, orient occupants to face daylight sources to take advantage of its blue light spectrum. And while computer monitors give off a lot of blue light, software that shifts their spectrum to orange in late afternoon hours should be used. The light level graph we saw earlier is a good example of how to program lighting in an office space. Similar equivalent melanopic lux graphs can be used as well. Tunable spectrum lighting allows electric light sources to adjust needed spectrum changes without significantly affecting illumination levels. Using banks of different temperature lights can be used if tunable spectrum lighting is not in the budget. By the way, some lighting automation systems are equipped with outside light sensors that can tune inside lighting to simulate the outside spectrum. Pretty cool. Of all the populations you deal with, the occupants of senior care facilities have the most to gain from circadian lighting. Most of the sleep disorders this group suffers is from a lack of daytime light. These facilities seldom have enough of the right kind of light, and the situation is made worse due to age-related changes to the eye that attenuate blue light. Whenever possible, these facilities should have easy access to outdoor areas for daytime light exposure. Activity areas should always have as much access to daylight as possible. Since falls are a major concern, lighting doorways and hallways makes navigating much easier. The Lighting Research Center recommends a circadian stimulus schedule that looks like this for common and activity areas. These requirements can be met with a combination of daylight and electric light. Lighting for healthcare presents unique challenges for accommodating diverse patient populations, as well as the need for 24-hour shift operation. Having distinctly separate lighting zones can allow for different circadian lighting schedules for day shift and night shift nurses, infants, patients, and visitors. Circadian light can allow more rest and recovery for patients while allowing adequate illumination for staff. Patient rooms should be on a normal daily circadian lighting wake-sleep schedule, while staff areas can be on a shift schedule. Since patients spend most of their time looking up, direct overhead lighting should be avoided in favor of indirect horizontal lighting. Nursing staff need adequate light to work with patients, but abrupt light at night should be red shifted with very low circadian stimulus values. The Lighting Research Center recommends several different lighting schedules depending on shift cycles. This lighting schedule is for a 2-shift, 12-hour schedule for day and night. The night shift is not a duplicate of the day shift, but gives workers more time to sync to an early part of the day's sleep cycle. Lighting for schools has fewer options. Any of you who have teenage children know that the circadian rhythms and sleep-wake cycles of children gradually shift as they get older toward late morning wake times and late onset sleep times. The early start times of highly structured school schedules leads to reduced sleep duration. By keeping students in classrooms all morning, they seldom get adequate exposure to morning light, especially during dark winter months. Therefore, exposure to adequate morning circadian light can mean the difference between learning and dozing. Unfortunately, the use of task lighting or computer screens to contribute to melanopic light is probably not an option, and access to outside light is usually limited since schools are relying more on display screens for teaching. Therefore, most of the circadian stimulus would need to come from overhead room electric light. To reach required vertical illumination levels will require the use of white or bright vertical surfaces and reflective horizontal surfaces. Circadian stimulus levels should start at or above 0.4 throughout the morning, gradually decreasing until the end of the school day. Classes which end late in the day should keep their circadian stimulus levels low with red-shifted light. By the way, students should be encouraged to use the night shift mode on their phones, since phones held close to the eyes contribute a lot of blue light at night, delaying the melatonin cycle. We have definitely covered a lot of material about LED lighting in this course. I started with the types of LED lights, typical packaging and installation, followed by lighting control system options for LEDs, including the new Power over Ethernet standards that I think will change how lighting is designed and installed. Then I got technical with how LEDs emit light and how they generate white light and the resulting unique spectrum, followed by a geeky dimming demo. I introduced a lot of acronyms about color and visible spectrum concepts, including black body radiation, color temperature, and coordinated color temperature. This let me talk about how LEDs perform dim to warm and tunable white, and how they are now able to simulate the natural cycle of light on Earth. Then we covered the discoveries of our circadian rhythm, the major rhythms we cycle through each day, and how blue light plays a part in keeping our rhythms synchronized through the hypothalamus. I covered the emerging research into recommended circadian light exposure levels, and how LED lighting can play a major role in maintaining our health and well-being. This was followed by techniques and design recommendations on new lighting strategies with examples of 4 typical environments. I hope this course generated a much greater awareness to the potential of new LED technologies, and I hope you found it potentially beneficial to your practice. Thank you, and please let me know if you have questions. You can reach me directly at graysonevans.consulting@gmail.com.